All right, so this is basically where we left off last time. So calculate the pH of a buffer solution that is zero point zero 0.05 molar benzoic acid and 0.150 molar in sodium benzoate. And you're given the Ka value of the acid here, which is 6.5 times 10 to the negative 5. So in this type of problem, you can use the Henderson-Hasselbalch approach as long as the condition is met. And that condition is the Ka value should be 100 times to 1,000 times less than the concentration of the acid or the conjugate base, right? Um, or you can also use the equilibrium approach, in which you find the Ka expression, you populate the ice table, and then solve for the pH. Right. So the first thing that we looked at is the equilibrium approach, in which we set up the reaction equation, in which the benzoic acid uh, gets ionized in water, H2O. So here's the chemical reaction equation. So you have benzoic acid reacting with liquid water to form hydronium ion and the conjugate base. And then you just start populating this ice table here. So the initial concentration of the acid is 0.05. Initial concentration of the hydronium ion is 0. And the benzoate ion, which is 0.15. And then you would proceed uh, normally. All right, and then we determine the equilibrium concentration as a function of x. And then you plug this into the Ka value, and you find the value of x, which is the concentration of hydronium ion. And from there, you can calculate the pH, because pH is equivalent to the negative log of the hydronium ion. And so that gives you 4.66. Or you can just use the Henderson-Hasselbalch approach. So this is basically the shortcut, right? Because it bypasses the ice table. So you don't have to draw the ice table and populate it. All you have to do is plug in the numbers into the equation. So here's the Henderson Hasselbalch equation, and we know what the Ka value is. It's 6.5 times 10 to the negative 5. So from there, all you have to do is take the negative log of the Ka to get the pKa, right? And then we add the log of the ratio. So the ratio here is the concentration of the base, which is basically the conjugate base, in this case, sodium benzoate, divided by the acid, which is benzoic acid. So that would be log of 0.15 divided by 0.05, or log of 3. Right, so plug in all the numbers here, and we get the same value for the pH, which is 4.66. Okay, so here's a little bit more of a challenge type of concept. So once we have a buffer solution, and remember that a buffer solution is a solution that resists the change in the pH. Okay, but it doesn't mean that the pH will not change when you add a strong acid or a strong base. There's still going to be a little bit of change in the pH of a buffer solution. What we're trying to say here is that a buffer solution has uh, a buffer solution has the capability to neutralize an added base or an added acid, right? If you were to compare this with water, just pure water, for example, then water doesn't have that same ability. And so adding even a small amount of an acid or a base will dramatically change the pH of that solution, but not for buffer solutions. Okay, so whenever we're calculating the pH change in a buffer solution, we have to break the problem into two parts. So the first part is using stoichiometry. So we're going to try to find how much of the acid is left, right? The acid component of a buffer solution or the base component of buffer solution after the added base or acid. Okay, so a stoichiometry calculation for the reaction of the added chemical, whether it's an acid or a base, with one of the ingredients of the buffer, right? So if you added an acid, then that acid will react with the conjugate base that's present in the buffer solution. And if you were to add a base, then that base will react with the acid component of the buffer solution. And the second part here is to basically either use the Henderson-Hasselbalch equation or the equilibrium approach. Okay, so an equilibrium calculation of the hydronium ion using the new initial values of the concentration of the acid and the concentration of the conjugate base. So here's an example, right? So we have a buffer solution that contains acetic acid. Right, so we have a buffer solution with a total volume of 1 liter, and this solution contains the acid acetic acid plus its conjugate base, which is the salts, right, sodium acetate. And you're also given the Ka of the acid, which is 1.8 times 10 to the negative 5. All right. And because the initial amounts of the acid and conjugate base are equivalent, then the pH of the buffer is simply equivalent to the pKa. Because if you were to use the Henderson-Hasselbalch equation, pH equals the pKa plus the log of the ratio, right? So if the ratio is equivalent to 1, then taking the log of 1 is basically equal to 0. And so pH is simply equivalent to the pKa. So that's what this is saying. So calculate the new pH after adding 0.010 mole of solid sodium hydroxide, okay, to the buffer. Okay, so that's the first question. The second question here is calculate the pH after adding the same amount of sodium hydroxide to 1 liter of pure water and see how the pH would change for pure water compared to a buffer solution. So the first thing that we want to do here is to break this problem, into two parts. And the first part is using stoichiometry, right? So we added solid sodium hydroxide, right? And this is the amount of sodium hydroxide that we're adding. And so sodium hydroxide is an example of a strong base. And a strong base, or any base, will react with the acid component that's present in the buffer solution. So we're going to set up our stoichiometry here, our reaction, right? So the sodium hydroxide will react with this hydrogen, right, which is present in the acid. So this is the acetic acid. So when sodium hydroxide reacts with hydrogen, it forms water. And then what's left is the conjugate base, which is going to be one of the products, the conjugate base, right? So before the addition of the sodium hydroxide, which is the base, the amount of moles of the acetic acid is 0.100. So we're going to write that down here, 0.100. All right, and we don't care about water because it's in liquid state. And then for the acetate ion, the initial concentration or initial amount in terms of mole is also 0.100. Okay. And then we're adding sodium hydroxide, which is 0.01. All right, and nothing here. And then after the addition, this sodium hydroxide will be consumed in the reaction, right? Because it's reacting with the acid, and so it's gonna get consumed in the chemical reaction. And so we're gonna subtract 0.01 from sodium hydroxide, right? And so now this becomes 0. we're also going to subtract 0.01 from the acid because it's reacting with the acid. And we will get 0.09. Okay. And because the sodium hydroxide is reacting with the acid, the hydrogen is being, it's being taken out by the hydroxide ion, right? It's taken away by the hydroxide. And so when hydrogen leaves this acidic acid, then you're generating more of the conjugate base, which is the acetate ion. So instead of subtracting 0.01 here, we're going to add 0.01. Again, you're generating additional number of moles of the conjugate base. And so add them together and we have 0.110. Okay, so here's a cleaner version. All right, so now we know the total amount of the acetic acid. All right, so the total amount of the acetic acid is 0.090. And for the acetate ion, it's 0.110. So now the second part of the approach is to use the equilibrium approach. Okay, so you can use the equilibrium approach or the Henderson-Hasselbalch approach. All right, so if we were to use the equilibrium approach, we're going to have to write the chemical reaction for the acidic acid in water. So again, acetic acid will get ionized in water to form hydronium ion and the acetate ion. So that's what we have here. All right, and then you're going to populate the ice table. So again, we would have 0.09. So you're basically just transferring this over here, transferring this on this side, and then the hydronium ion initially would be 0. Okay, so that would be 0.09 here, 0.110 here, minus x plus x plus x. All right, and then find the equilibrium as a function of x. There you go. And then here's the cleaner version. Okay, so from here you can use, you can generate the Ka expression so that we can find the value of x. So here we have Ka equals 1.8 times 10 to the negative 5. So, as I've mentioned in the past, if the Ka value is less than 10 to the negative 3, right, if Ka is less than 10 to the negative 3, then we can just drop the x here. So we're going to drop this x and drop this x because this is sort of the approximation method. Right, so the Ka expression is concentration of the hydronium ion times the concentration of the conjugate base divided by the concentration of the acid. All right, and then we're given the Ka value here, so it's 1.8 times 10 to the negative 3 or negative 5. So the concentration of hydronium is x, right, times the concentration of the conjugate base, which is 0.110, and divided by the concentration of the acetic acid, which is 0.090. All right, and then you just find X. Isolate X here by itself. So we have roughly 1.5 times 10 to the negative 5. All right, so this would be the concentration of the hydronium ion. All right, and again, you can just plug this into the equation of 4 pH. This is negative log of concentration H3O plus. Okay, and here's the cleaner version. And taking the negative log of 1.5 times 10 to the negative 5 gives you the pH value, which is 4.83. So again, this is using the equilibrium approach. We could also just go ahead and use the Henderson-Hasselbalch approach, right? Using that equation. The reason why we can use that is because the Ka value here, okay, is a lot less than the amount of the salts, the salt and the acid. And so we can just plug it into the pH equation. pH equals pKa, okay, plus the log of the conjugate base. So the concentration of the conjugate base here is 0.110 divided by the amount of the acid, which is 0.090. Okay, and when you plug this in, so again, pK is 4.74. Right, plus the log of this ratio. And you will also get the same pH here, 4.83. All right, so here's the cleaner version. Right, using the same approach here, Henderson-Hasselbalch, using the equation, and we get the same pH value, which is 4.83. All right, what about the second question here? It says, for comparison, calculate the pH after adding 0.010 mole of solid sodium hydroxide. So basically the same amount of sodium hydroxide, but instead this is going to be in pure water. And so so from here you can actually calculate the pOH first. Okay, so we will calculate pOH first. Right, pOH is equivalent to the negative log of the OH concentration. Right, so how do we find the concentration of the sodium hydroxide? Well, we're given the number of moles, right, of the solid sodium hydroxide. We're also given the volume, and so we can calculate the concentration of OH minus. This is equivalent to 0.01 mole divided by 1 liter. So the concentration is 0.01 molar. So you plug this number in to this equation. Negative log of 0.01 gives you the pOH, and then from pOH you can get the pH. So pH is equivalent to 14 minus pOH. So here's the cleaner version. Right, so without the buffer, we get a pOH of 2.00, and then subtract 2 from 14, we get a pH of 12. So if you were to compare this, right, so the pH of pure water is 7. So we have pH 7 to pH 12. So that is a huge change in pH compared to the buffer, right? The pH of the buffer initially, before the addition of the sodium hydroxide is 4.74, and then after the addition, it changed into 4.83. So there's not very much change. All right, so now let's make a transition here and talk about basic buffers. I'm not going to cover this in great detail because the examples are very similar to acidic buffers, right? So the difference between acidic and basic buffers is that basic buffers have pH greater than 7, and so you can create a basic buffer by adding a weak base with its conjugate acid or a salt of its conjugate acid. Okay, so an example here is if you were to mix ammonia, which is a base, with ammonium chloride, which contains the conjugate acid in the form of a salt. Okay, so the conjugate acid here is NH4 plus. Right, so if you were to combine this with the chloride ion, then you have a salt, right, an ionic compound. And so mixing the two together, you have a buffer solution, a basic buffer solution in which the pH is greater than 7. All right, so what makes a buffer effective, right? How do we define effectiveness of a buffer solution? So an effective buffer should be able to neutralize moderate amounts of the added acid or base. But of course, there's a limit to how much you can add into the buffer solution before the pH significantly changes. Okay, so before we can talk about effectiveness, we're gonna cover two terminologies here. The first one is buffer capacity, which is the amount of acid or base a buffer is able to neutralize. Okay, that would be the buffer capacity. Buffer range, on the other hand, is the pH range in which the buffer can be considered effective. And the effectiveness of a buffer depends on two things. The first one is the relative amounts of buffer acid and the base, meaning the concentrations, okay, the relative concentrations of the acid and the base, and two, the absolute concentrations of the buffer acid and the base. Okay. Okay, first let's focus on capacity, buffer capacity. So again, buffer capacity is the amount of the acid or base that can be added to a buffer without causing a large change in the pH. Right? So you don't want a significant change in the pH. The buffer capacity basically increases with increasing absolute concentration of the buffer components. So it's a lot better to use a concentrated buffer, okay, than a dilute buffer. The reason why is because the higher the concentration of the buffer components, the more effective the buffer is. Okay, so make sure that you remember that. More concentrated equals more effective. Okay, this is going to be a more effective buffer. The reason why is because a concentrated buffer is able to neutralize more acid or base than a dilute buffer. Okay, so let's say this concentrated buffer contains 0.5 mole 0.5 mole of acetic acid. Okay, HC2H3O2. All right. And whereas this dilute buffer contains 0.05 mole of the acid. So if you were to add 0.1 mole of base, right, then the concentrated buffer will be able to neutralize this entire amount of the base. Whereas the dilute buffer, you only have 0.05 mole of the acid, and so it's not going to be able to neutralize the added base completely. And so you're basically destroying the buffer here, right? The dilute buffer will be destroyed. All right, so the concentrated buffer then is a more effective buffer than the dilute buffer. All right, a buffer will be most effective when the ratio between the acid and the base is equivalent to 1. So in other words, the concentration of the acid is equivalent to the concentration of the base. Okay. So here's an example of a problem illustrating this concept. All right, so we have two buffer solutions. Okay, we have solution 1 and solution number 2. In solution number 1, notice that the amount of the acid is equivalent to the amount of the conjugate base. Okay, so the ratio here is 1 to 1, whereas in solution number 2, the ratio is not 1 to 1. All right, so how do we prove that solution number 1 is more effective? Well, let's take a look. So let's say that we're adding sodium hydroxide into the buffer solutions, right? And this is the amount of sodium hydroxide that we will add. So we're adding 0.010, and so we will subtract that from the acid, right? And then add it into the conjugate base. So subtracting 0.01 from 0.1 gives us 0.09, and adding 0.01 to 0.1 gives us 0.110 mole of the conjugate base. So using the Henderson-Hasselbalch approach, or the Henderson-Hasselbalch equation, pH equals pKa, which is given here, it's 5, plus the log of the ratio, which would be 0.110 divided by 0.09. Okay, so that's how you would set up this equation. And then we can do the same thing for solution number 2, right? So we're adding 0.010 mole of sodium hydroxide into the buffer solutions, and so it will react with the acid. So solution number 2 contains 0.18 of the acid and 0.020 of the conjugate base. So we're going to subtract 0.01 from 0.18, and that gives us 0.17 for the acid and 0.030 for the conjugate base. So our pH then is equivalent to pKa, which is again 5.00 value plus log of the ratio. The ratio here is the conjugate base 0.030 divided by 0.17. All right. So this is how you would set up the Henderson-Hasselbalch equations. So here's the cleaner version. So looking at solution 1, the pH changes to 5.09. So there's a little bit of increase in the pH, right? So the pH initially was 5.00, right? So adding the sodium hydroxide resulted in the increase in the pH to 5.09. And so you can calculate the percent change here. Percent change is basically equivalent to 5.09 minus 5 divided by the initial pH multiplied by 100%. Okay, and this is how we can compare solution 1 from solution number 2. Here's a cleaner version. So for solution number 1, the percent change in the pH is only 1.8%. Looking at solution number 2, we'll do the same thing. So the pH changed from 4.05 to 4.25. Okay, and looking at the percent change here, we get 4.9%. So 1.8% versus 4.9%. You see that solution 1 is more effective in neutralizing the added sodium hydroxide. All right, and one last thing here. A buffer will be considered effective when the ratio between the base and the acid is between 0.1 and 10. All right, so for example, if the concentration of the base is equivalent to 10, right, and the concentration of the acid is equal to 1 molar. All right, so the base acid ratio, 10 divided by 1, gives you a value of 10. All right, and let's say it was reversed. Let's say now the concentration of the base was 1. Concentration of the acid is 10. 1 divided by 10 would give you the lower limit here, which is 0.1. Okay, so a buffer will be effective when as long as the concentrations do not differ by more than a factor of 10. Right, so right here, the difference here is basically no more than a factor of 10. All right, and here's another concept here. A buffer will be most effective when the concentration of the acid and the base are high. Okay, so this is related to the first one that we looked at, right? Concentrated buffer versus dilute buffer. It's a lot more effective to use a concentrated buffer than a dilute buffer. So here's another example illustrating this concept. So let's look at solution number 1. So we have solution 1 here that contains 1-to-1 ratio between the acid and the conjugate base at a concentration of 0.5. Okay, whereas solution number 2 here contains tenfold less, right? So this is 0.05 mole of the acid and 0.05 mole of the conjugate base. So you can see that by adding a base into the buffers, how would that change the pH? And what is the total percent change in the pH? So we'll do the same thing here. So we're going to subtract 0.01 of the sodium hydroxide from the acid. So 0.01 minus 0.5 gives us 0.49 mole of the acid. So that means that our acid here is in excess, right? And then because this will generate conjugate base, we're going to add 0.01 to 0.5, and that gives us a total of 0.51 mole of the conjugate base. And then from here, we're going to plug in all the numbers to this Henderson-Hasselbalch equation. So pH equals pKa plus log of 0.1 divided by the acid, which is 0.49. All right, again, pKa is already given here, so you just plug it in. All right, here's a cleaner version. plug the numbers into the calculator and we get pH of 5.02. So you can see that our initial pH was 5.00. After adding 0.01 of sodium hydroxide, the pH changed only slightly to 5.02. So you can calculate the percent change in the pH here, and we get 0.4%. And then we're going to compare solution number 2 here using the same approach. And you can see that the percent change is 3.6% versus 0.4%, proving that more concentrated buffers are more effective in neutralizing the added acid or the added base. Okay, so now let's talk about the buffer's pH range. Okay, so remember again that a buffer will be considered effective when the ratio is between 0.1 and 10, right? The ratio between the base and the acid is between 0.1 and 10. So if we were to substitute these values, right, into this equation, right, so we can have a lower limit, right, and an upper limit in terms of the pH. All right, so for the lower limit, we would plug in 0.1 for the ratio here. All right, so that would be pH equals pKa plus the log of 0.1. And for the upper limit, same thing, pH equals pKa plus the log of 10. So using this, pKa log of 10 is basically equivalent to 1. Log of 0.1 is equivalent to -1 or -1. All right, so that means that an effective buffer will have a pH equivalent to pKa of the acid plus -1. So that would be considered effective buffer. So here's a cleaner version. So again, plugging in the values here for the lower limit, we have pKa -1. Plugging in the upper limit, we have pKa plus 1. So an effective pH range of a buffer is when the pH is equivalent to the pKa plus or -1. And so whenever you're choosing an acid to generate a buffer solution, you want to choose the acid whose pKa is closest to the pH of the buffer that you want to make. Okay, so let's see if I have an example here. All right, here's an example. Which acid would you choose to combine with its sodium salt to make a solution buffered at pH 4.25? And for the best choice, calculate the ratio of the conjugate base to the acid required to attain the desired pH. All right, so we want to make a buffer solution that has a pH of 4.25. So according to the previous slide, we want to choose the acid who has a pKa value closest to the pH, right? So chlorous acid has 1.95, nitrous acid has 3.34, formic acid has 3.74, and hypochlorous acid has 7.54. So the one that's closest to 4.25 is the formic acid. So this is the acid that we want to mix with its salt of conjugate base to prepare this buffer solution that we want. Okay? So now the second question, calculate the ratio of the conjugate base to the acid required to attain the desired pH. So we know the Henderson-Hasselbalch approach or equation. pH equals pKa plus the log of the base, right, divided by acid. So this is our ratio here. So pKa is 3.74 plus the log of, I'm just going to simplify this and write ratio because that's what we're trying to find. Calculate the ratio. Right, and so the desired pH is 4.25, so the desired pH here is 4.25. All right, so all we have to do now is solve for ratio, right? We'll say, let's say X is equivalent to the ratio here, okay? So 4.25 minus 3.74 equals the log of X. Okay, again, X is equivalent to ratio. Okay, and in order to get rid of the log here, you raise this entire thing, right? So 10 and raise it to the number. So 10 to the difference here, 4.25 minus 3.74 is equivalent to X. Okay, so this is how you would find the ratio here. Here's a cleaner version. So here's the Anderson-Hasselbalch equation. Plug in the values. pH equals 4.25, pKa of 3.74, and take the difference between the two numbers, which is 0.51, and then 10 raised to the 0.51 will give you the ratio, which is 3.24. All right, so we're going to stop there, and this is going to be part 2, the end of part 2. We'll continue part 3 and start on titrations.